Hello everyone, welcome to my YouTube channel. My name is Rohan. In this video, we will discuss about fuzzy groups, fuzzy subgroups, and fuzzy abelian groups, and also we will explore the concept of fuzzy cosets. So, let's start our video. Before moving ahead, let's introduce just recall the basic things, which is what is Cripps sets and what is a group. The Cripps set is a collection of elements where each element either completely belongs to the set or not, and the group means non-empty set G comma star is said to be group if it satisfies they satisfies closure property, associative property, identity, element property, and inverse properties. Just see here. This star means any binary operation we can consider. Next is again some basic things are there for these sets definitions. Let's go to this side definition. For this set assigns a degree of membership ranging from 0 to 1 to each element in the set. There is an example, so we can consider the set of student heights. A fuzzy set tall students might assign a membership value of 0.8 to student who is 6 feet tall, indicating a height of degree of tallness. Here, just consider, here consider we assign this in this example we assign 0.8 membership value for 6 feet student. So this is not complete value. Just we can assign another value. So suppose 6.5 feet student. We can assign for this value is 1. So in this type we can imagine this again. Fuzzy groups are just a normal group thing into fuzzy logic. So let's come to our main topic, that is fuzzy groups. Definition: fuzzy group means what? Fuzzy group is a group whose uh, elements have a fuzzy membership value, and also that satisfies the closure property and as well as inverse property. So what we define closure property? Closure means what? The membership value of product or sum of two elements is at least the minimum of their individual membership values. Means what? Here a of x y we take here product. So we take any product or sum. So we take here product a of x x into y is greater than equal to minimum of a of x or and a of y. So just remember these things. Don't confuse. So I will explain in detail with the example with the help of examples. Next is inverse property. How to define this? The inverse property holds meanings. Every element has this inverse with the same membership value. Just in simple things. Let's see here. We can consider element A and the star. For star, we consider addition operation. So let's consider A element. So for addition, the inverse of A, this should be identity A plus AG by binary operation, and this its inverse is should be equal to its identity elements. Means we can take any operation for this, and this is equal to identity element of any binary operations. So let's go ahead. See here example. This is question. Check whether the fuzzy set A is the group G under addition will form the fuzzy groups. The fuzzy membership functions A of x is defined as there are given fuzzy membership functions. So we need to check this is a group or not. So see here what is the solution. First is we need to check the any membership value is its sum is greater than equal to or not. So see here we take in general x and y values. So a of x we take additional operation. We can take addition plus product of any two membership values. So a of x plus y is should be greater than equal to minimum of its individual membership values. A of x comma a of y. So I will take two values x for x for 1 and y for 2. So a of 1 plus 2 is should be greater than equal to minimum of what is the membership value of 1 and 2? 0.8 and 0.6. Then a of 3 is should be greater than equal to minimum value of 0.6. So what is the membership value of 0.3? 0.7. So 0.7 is greater than 0.6. So this satisfies closure property. Then next we need to check inverse property. What is inverse property? We consider for one. So inverse property means we consider 0.8 membership value 0.8 plus minus 0.8 is equal to 0, and 0 is the identity element of some additional operation. So then next fuzzy subgroup. Fuzzy subgroup means what? Fuzzy subgroup is a subset of fuzzy group which is also satisfies closure and inverse properties. So like fuzzy group, there is a definition of fuzzy subgroup. So again we move ahead. Same example I will take here for fuzzy subgroup. They are same things, but if any subset is not satisfy closure property, then we cannot say that this is a subgroup. So I will go ahead. The next thing is fuzzy abelian groups. What is mean by fuzzy abelian group? This is same fuzzy abelian group means a group which is fuzzy group where additional property it is follows, that is commutative property. Means we can say that fuzzy abelian group follows closure property, inverse property, and also commutative property. So let's see one example of fuzzy abelian group. This is same example. Plus we need to check for commutative property. We will follow this same process for fuzzy abelian group. We should satisfy closure property. We need to satisfy your property, as well as we need to satisfy commutative property. So let's see first commutative property. I will take membership values 1 and 2. So a of x plus y is should be equal to a of y plus x. So a of 1 plus 2 is equal to a of 2 plus 1 is equal to 3. A of so additional things if the group should satisfy closure property, inverse property, and commutative property. So we can say that this is it is a abelian group. So I will stop here. The next remaining part will call my friend Praful Olekar. So thank you.
Hello, my name is Praful. Rogan has covered the already fuzzy subgroups and groups. I have covered the next parts in this session. What is the properties of fuzzy subgroups? In this topic, G stands for a group with identity and 0 to 1. In between 0 is less than or equal to lambda and J is a micro and J is equal to 1. By Fuzzy set of a G, we mean a mapping of G to the closed interval 0 to 1. In this section, we present some basic properties of Fuzzy subgroups. First, a definition. Let A be a Fuzzy subset of G, then A is called a Fuzzy subgroup of G. If for all x and y belong to G, the first property is A of x into y is greater than equal to A of x and A of y. And second is A of x inverse is greater than or equal to A of x. Next, properties of normal subgroups. Let A be a Fuzzy subgroup of G and A is called a Fuzzy normal subgroup of G. If for all x y belongs to G and x into y into x inverse is greater than or equal to A of 1. The next Fuzzy group homomorphism. A Fuzzy group homomorphism is a function that preserves the structure between Fuzzy groups. The membership values of the element is equal to the membership value of the original element. For example, a mapping between a group under addition modulo 4 and a group under addition modulo 2, where the membership value of each element is 1 and is a Fuzzy group homomorphism. For example, consider the following example of the Fuzzy group. Consider the following example of the Fuzzy groups: Z4, A micro and Z2, neta of x is equal to 1. For all x belongs to Z4 and neta of y is equal to 1. For all y belongs to Z of 2. Define f from Z4 to Z2 by f of 0 is equal to f of 2 is equal to 0 and Z2 of neta where f of 1 is equal to f of 3 is equal to 1. Then f is a group of homomorphism from Z4 to Z2. Define alpha from micro of Z4 to neta of Z2 as alpha of micro of x is equal to 1 for all x belongs to Z4. Then alpha is a bijection and f comma alpha is from Z4 comma alpha micro to Z2 neta is a Fuzzy group of homomorphism. This is the example of Fuzzy groups. Next one is Fuzzy cosets. There are two types of Fuzzy cosets. Left and right cosets are generalization of cosets in normal group. They are obtained by multiplying elements of a Fuzzy group by elements of Fuzzy subgroup. An example for a Fuzzy subgroup: for a Fuzzy subgroup, left and right cosets for specific elements can be calculated using the formulas. The properties of left coset and right cosets of A. Let A be a lambda of micro Fuzzy subgroup of G and A belongs to G. Define Fuzzy subsets. A composition A and A composition A of G is that A composition A of X is equal to A of A inverse into X is a or lambda and micro for all X belongs to G. This is the A of A composition A is the left coset and this is the A composition A is the right coset of A. This This is the property of left coset and right coset. Then applications of fuzzy groups. First, used in AI, fuzzy logic finds applications in AI for reasoning and decision making under uncertainty. Second application is control systems. Fuzzy controllers manage complex systems like robots, vehicles, and industrial processes. Third application is robotics. Fuzzy logic enables robots to adapt to changing environments and uncertainties. Last one is machine learning. Fuzzy logic contributes to machine learning algorithms for pattern recognition and classification. So conclusion, fuzzy groups extend normal groups by incorporating membership degrees. Second, fuzzy groups further satisfy the commutativity property. Third, fuzzy subgroups adhere to closure and inverse properties within the fuzzy group structure. Fuzzy group homomorphisms reserve structure between fuzzy groups. Fuzzy cosets allow the formation of fuzzy groups.